So this next unit, first one of the semester, I wanted to do something different. This isn't really a really intensive algebra unit. It's kind of fun, honestly. So we're going to look at probability and statistics, more so probability. Basically, if you think of like all the games that you play as a kid, like thinking specifically of like any game where you have to roll a die, whether you're playing Clue or Monopoly or anything that involves cards, Uno, or if you're just playing like a game of Rummy with a regular deck of cards. There's just some neat things that kind of happen mathematically behind the scenes on those games that you just probably weren't even really aware of. Um, Basically, we're going to calculate the theoretical probability. So, like mathematically, what should happen when you roll a die? Mathematically, what should happen when you flip a coin? Real simple events. The hardest part of this is going to be the notation and how it looks, how it's presented to you when I ask a question. But I think that's pretty much my focus today. Is not so much the math of it, it's the notation of it. So probability is basically the chance that an event is going to happen. Sometimes it's written as a percentage. Sometimes it'll be written as a fraction. Most of the time when we do it, it'll be written as a fraction. But a lot of the stuff you kind of already know just from being, your life experiences. Like what's the probability that when you flip a coin, it'll come up ahead? Well, pretty much everybody will tell you, oh, that's 50-50. Well, yeah, yes and no. It just kind of depends on what the question is being asked. So the probability you could get ahead, it's 50% sure, and then the other 50% in that 50-50 is the 50% of the time that you fail that you get a tail. So a probability actually kind of shows you both sides of the event, the successful stuff that you want to have happen and the unsuccessful stuff that doesn't happen. Now, the more possible outcomes there are with that, the different your probability is going to look. So first things first, I want to get into how this is presented to you when I ask a question. So again, theoretical probability, you could flip a coin 1,000 times and you would expect to get 500 heads, 500 tails. Theoretically. Now you could actually, and I'm sure it's happened somewhere in the history of the universe, you flip that coin 1,000 times, there's a possibility you could get 1,000 heads in a row or 1,000 tails in a row. So that's what I mean by theoretical. It's what should happen instead of what actually happens. Okay, so the way these things are going to be presented to you when I ask a question is this big capital P out here, right? You're going to have, the probability, and then in parentheses, you're going to have the event that we want to have happen. So like if you flip a coin, it'll say something like, what's the probability that you get a head when you flip a coin? And your answer is going to be given to me in a fraction. So the way you format this fraction, you have to kind of think of, this is more a mental exercise than an arithmetic exercise. You have to think of like all the possible things that could happen. So when you flip that coin, how many successful outcomes are on that coin? So in this case, how many heads are there on that coin? Right? If it's just a regular coin, there's one head listed, and then the total possible outcomes when you flip that coin, it could either come up a head or come up a tail. There's two possible outcomes. Now, pretty much every single coin has some sort of variation on that. Like, I can't speak to coins in like other countries and stuff, but there's a one side and then another side. So you flip a coin, maybe it's a head, maybe it's some sort of animal caricature, whatever. So coins are kind of boring when it comes to probabilities. Dice, specifically when you start looking at paradise, but we're going to look at just one here. So the probability, and I want to just kind of reiterate this here, the probability, you're flipping a coin, it says, flip a coin. The probability of getting a head, there's one head out of two possible outcomes on that coin, head or tail. The probability of getting a tail, well, that's half again, it's the other half. If you divide those out and look at the percentages, if you take 1 divided by 2, that is 0.5 or 50% if you want to change that to a percentage. That's what I was talking about earlier when people say, whoops, I don't know why that decimal's there. When people say 50-50, there's a 50% chance you get ahead, 50% chance you don't get ahead. That's the 50-50 of it. Now, Consider a scenario where you're playing a board game and you're rolling a regular 6-sided die. There are other sided ones out there. If you've ever played any like role-playing games, you might have a 20-sided die or whatever, but we're sticking with like regular board game dice. So when you roll a die, you have 6, I said 6 and wrote 6. You have 6 possible outcomes when you roll a regular die. All right, 1, 2, 3, 4, 5, 6. So I'm going to ask you some questions here just based on that individual die. Tomorrow we'll look at when you roll a pair of die, and that kind of really complicates and makes things a little more interesting at the same time. So the probability that you can roll that single die and get a 2. The question is, how many 2s are on that die? Well, the answer is 1. And then for the denominator of that fraction, how many possible outcomes were there? Well, there's literally 6 outcomes. So the probability that you could roll a die and get a 2 is 1 out of 6. I don't want you guys changing these to percentages. I just did that to kind of illustrate the whole 50-50 thing up here. When you set up a probability, leave it as a fraction. The only thing that I'm going to ask is that you reduce your fractions. Okay? So the probability that you can roll an even number, well, there's a 2, a 4, and a 6. Those are even numbers out of 6 possible. So I'm going to reduce that down to 1/2. Now, if you think about that, that makes sense. Half of the numbers are even, the other half of the numbers are odd. So it kind of makes sense that your probability is a half. All right, and then the probability of rolling a number less than 7. We'll take a look at all your possible outcomes here, right? Every single one of those possible outcomes, the 6 possible outcomes, would be considered a success, right? Because they're all less than 7. I threw that question in here specifically for this situation. When you reduce that, you get a probability of 1. That is 1 as in 100%. It is a 100% guarantee, bet money on it, that you're going to get a number less than 7. It's a guarantee. It's always going to happen. And again, just to kind of illustrate, 100% of the time. Okay, so, but again, just as a fraction, 6 over 6 reduces down to 1. You can give it as 1 over 1, but whole numbers are acceptable there too. And that leads into this. So if you consider that situation of rolling a die, right? I rolled a die. I've got 6 possible outcomes. 1, 2, 3, 4, 5, 6. So the probability of rolling something less than 7, again, that's pretty much guaranteed. It's 6 out of 6, has a probability of 1. Now, if I ask you if this is just a regular die, what's the probability of rolling an 8? How many 8s are on that die? Well, I've never seen a single die that had an A on it. So there's 0 successes out of those 6 possibilities. It's not going to happen at all. So these are what I'm calling special probabilities. You've got the possibility that something is always going to happen or that it's never going to happen. Everything else in between is a fraction greater than 0 and less than 1. So those are all your possible probabilities. 1 being guaranteed, 0 being never. All right. Another kind of staple in probability is a bag of marbles, and this is going to be it. This is the last couple questions here. So we're going to reach into this bag of marbles, and it looks like there's 1, 2, 3. Let's make this a little bit easy here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 marbles. So all of these probabilities are going to have a possible outcome of 20. Okay, the probability that we get a blue out of this, well, there's 6 blues, 6 out of 20, reduce it down, 3/10. So if we reach into this bag, we should expect about 30% of the time to be able to pull out a blue marble. Similarly with the red, 1, 2, 3, 4, 5, 6, 7, 8, 9, there's 9 reds out of 20, that doesn't reduce, and not blue. What that means, take a look over here at this bag of marbles. How many of these marbles over here are not blue? Well, there were 1, 2, 3, 4, 5, 6 blue. That means that 14 of them are not blue. Reduce it down, 70%. And again, those probabilities kind of work hand in hand. If 3/10 of the time you can get a blue, 7/10 of the time you won't get a blue. they should kind of complement each other that way if you're asked questions that go in that same vein.